Ahoy shipmates! Welcome to a video on trigonometric ratios this time. A new chapter, a new day. So we're going to assume here that you're okay with the idea of SOH-CAH-TOA using trigonometry in right-angled triangles. And we're going to extend this today into having a look at also what you should have seen from GCSE before, and no doubt have seen, the sine and cosine rule, including some proofs of that too. And we're going to finish off with a slightly harder compound question using trigonometry. So this is more or less a warm-up from the higher tier GCSE bit of trigonometry, which you should have seen before. But because you might not have touched this stuff for a while, we're going to have a warm-up which is going to be very easy going in terms of just refreshing your memory from GCSE trig. So, like I say, here are the warm-up questions. Questions 1 and 2 in particular should be quite easy going. I hope so anyway. If not, this is your chance to just blow away the cobwebs and get up to date again. Question 3 and question 4, just a bit different. So let's have a look now and work through together the solution to question 1. So question 1, we have triangle ABC. It's right angled with angle at B being 90 degrees, the angle at A being 30, and the length of AB being 2√3. As shown in this diagram. So part A, using trigonometry, we have to find the length BC. So just to remind you from GCSE, which you should know already of course, the SOH-CAH-TOA triangles. So depending on what teacher you had at GCSE, each teacher has their own way of explaining things. This is how I tackle this question. So what I would do first of all is label the sides opposite, adjacent and hypotenuse accordingly. So the opposite side is always the side opposite to the angle in question. So opposite to the 30-degree angle we've been given is CB, and so that's the opposite. The adjacent side is the side that isn't the hypotenuse or the opposite. So that's going to be the adjacent, because the longest side, the hypotenuse, which is opposite to the right angle, is this one here. So I'm going to label that one H. Next, I'm going to think about what I know and also what I want to know. And so what I know already is AB, which is 2√3, which is the adjacent side. So I'm going to highlight A for adjacent in each of these triangles. Next, I'm going to highlight what I want to know. Now, I want to find the length BC, which is this side here, which is the opposite side. So likewise, I also highlight the O. I then pick whichever triangle is the most colourful and pretty. So which one have I coloured in most of? I've only coloured in one thing on the SOH triangle, only coloured in the A on the CAH. However, the TOA, the TOA triangle, I've coloured in 2 bits, the O and the A. Therefore, this tells us that we're going to be using the TOA triangle, where T stands for tan of the angle in question. So, based on this for part A, I'm going to write T for tan of the angle in question, tan 30 in this case, equals O over A. O is CB, and A is 2√3. So just colour coding that. O is the length CB, and AB is 2√3. So we can easily rearrange this to work out what the length CB is. So therefore CB is going to be 2√3 multiplied by tan 30. So let's get the class quizzes out just to be absolutely sure. So 2√3 multiplied by tan 30, close brackets. That gives us a length of exactly 2. And so this one here has a length 2. So that's what BC is. Then part B, it says hence use Pythagoras' theorem to find the length AC. And so for part B, AC, hypotenuse squared, is this side squared plus that side squared. So it's going to be 2√3 squared plus 2 squared, and all of that square rooted. So again, use the class whiz to calculate this with no doubt. So we're going to have 2 root 3, all of that squared, plus 2 squared, which is obviously 4. You could just put 4 in if you'd prefer. And that gives us a length of exactly 4. And so that's question 1 sorted. So we can now move on to question 2. Question 2, very similar to question 1. This time we have triangle DEF, which is a right-angled triangle, and we've got this information described here, but it's included in this diagram anyway. So I'm just going to skip right in to part A, find the angle theta using trigonometry. So again, let's just remind ourselves of the SOH-CAH-TOA triangles. Here they are. So let's work out what we know in relation to this angle. We need to find theta. Opposite to the angle theta is the side DF, which is 0.5. So I'm going to label the opposite side O for opposite. Hypotenuse, the longest side, I'm going to label H for hypotenuse. The other side has to be A. And so we know the opposite side, so we're going to colour in the O in each of these triangles. We also know the adjacent side, which is 1.2. So I'm going to colour in A for adjacent. In the same way as question 1, we use whichever triangle is the most coloured in. So of the SOH-CAH-TOA triangles, the one which has been coloured in the most, 2 items coloured, is TOA. So again, it's going to be using the tangent function. So for part A, remember when we're finding angles in trig, we use the shift, sin, cos or tan buttons. So in this case, because we've circled T for tan, theta is going to be tan to the minus 1 inverse tan of the opposite divided by the adjacent. So that's going to be 0.5 divided by 1.2. So again, we can just use our calculator to do this for us. So shift tan to get the tan minus 1, 0.5 over 1.2. And we get for this to 3 sig figs, 22.6 degrees. So that's our answer for part A. For part B, it says, hence find the angle DFE. Well, DFE is this angle here at the top. So now we've worked out theta, we know this is 90, we can just use the angle sum of a triangle to work out DFE. And hopefully you'll remember that the angles in a triangle always add up to 180 degrees. So we can say here that DFE must therefore be 180 minus the other 2 angles, so minus 90 and minus the 22.6 whatever we just worked out. So obviously we rounded it off to 22.6, so we can just use the answer stored in our calculator and round off at the end. So I'm going to leave this stored in the calculator as the ANS. So ANS equals, there you see it's stored for us. So DFE is 180 minus 90 minus 22.6 whatever, which is stored in the answer button. So we get to 3 significant figures, 67.4 degrees. And that wraps up question 2. Question 3 is a weird one, but a very nice question. So it's one of these questions where it's bleeding obvious when it's mentioned to you, but it might not be so obvious if you've not thought about it in any depth. So I'm going to reveal a little tip to you to work this one out if you're not sure where to begin. And like I say, once I tell you, it'll be obvious to you. In the same way that if I were to ask you, which way does the Queen's head face on a 2p coin, or which arm is held aloft by the Statue of Liberty holding the torch, You might have to think twice about it, but when you see a picture of either the coin or the Statue of Liberty, it seems just so obvious. How could you ever have doubted yourself? So the fact I'm getting at here is this one. So the longest side in a triangle is always opposite to the largest angle, and the shortest side in a triangle is always opposite the smallest angle. So if you draw a few triangles, it just is really, really obvious. But it's one of those things where if you don't consider things, it might not seem also obvious at all. But once you know this, it's a trivial question. It couldn't really be any easier. So all we need to do now is to pick the shortest side, which is this 2.66, and match it to the smallest angle, which is 33.56. Next, we pick the largest side and match that to the biggest angle, like so. And finally, the middle angle matches to the middle side, and that's all there is to it. So this is very useful to know and to be mindful of, this little fact. It's always true, but it's one of those things where if you don't consider it before and never really see that connection, it might not seem so obvious to you. But please make a note to remember this from now on. Finally, question 4, a bit of just general algebra revision. Find the set of values of x for which x squared minus 7x minus 18 is greater than 0. So for this one, we can just see if this one factorizes, which it does. So two numbers that multiply to make minus 18, and when we add them give us minus 7, that's going to be positive 2 and negative 9. So we can factorize the left into x plus 2, x minus 9, which must be greater than 0. So we can see here the critical values, in other words, the values of x which would make this expression equal to 0, and when each of these brackets would equal 0 in turn. So if this bracket were equal to 0, x would be negative 2, and for this bracket being equal to 0, we'd have where x equals 9. And if we're sketching a quadratic inequality, if we're trying to solve, a quadratic inequality, I'd always suggest to sketch a graph of it and then inspect whereabouts the graph is either above or below the y-axis as required. And so for this one here, a graph of x versus x squared minus 7x minus 18, we can plot. So if I just imagine that y equals x squared minus 7x minus 18, I can plot this, now know that the critical values are negative 2, say somewhere here, and positive 9, somewhere, say over here. So if I were to plot this, I'd have something looking a bit like this. And we want it to be greater than 0. So underneath the x-axis, this expression is less than 0, which we don't want. We want it to be greater than 0, and so we're after this bit of a graph here, and this bit beyond 9. And so the regions we're wanting are where x is less than negative 2, or where x is greater than 9. And those are the two regions which satisfy this inequality. In other words, these two inequalities are the solution to this general inequality here. And that concludes our warm-up for today. Now we've done the warm-up, it's time for the main course, if you like, the cosine rule and the sine rule. So you will have seen these at GCSE. I want to just remind you of how these results can be proven so they can be used in future. You could just remember them by heart and not worry about proving them. That will do for your exams, but I think if possible, if a result can be shown, it should be shown where it's not so hard to do so. And these are relatively simple results to show you. So which one shall we pick? The cosine rule or the sine rule to do first? I've gone for the cosine rule. So first of all, I want you to consider generally this scalene triangle ABC. shown below. The proof I'm going to offer here is a more complicated proof than what the Edexcel book shows, because the Edexcel book proves the cosine rule as well in its pages. Now the proof I'm using is more complicated. Why do a more complicated proof if a more straightforward one exists, you may rightly wonder? Well, it's a good excuse for me to introduce a very, very important trigonometric identity, which you'll see countless times in year 13. So I'm just trying to give you a bit of a head start and give you this identity. You might know it now, of course, but chances are you've not known this result until now. So what is this result? Let's have a look. So I'm just going to highlight this a powerful result. So here's a triangle. I'm going to say now it's a right angle triangle. I'm going to say its angle here is theta, hypotenuse is 1. So considering this, let's just think about how we could define the sine function for this triangle. So just to remind you, for SOH-CAH-TOA triangles, this is going to be labelled side x. Over here, the opposite side, I'm going to label this y. And like I say, to remind you of the SOH-CAH-TOA triangles, here they are as well. And so what would the sine function for this triangle be? Well, we'd have sine theta equals the opposite side divided by the hypotenuse. The opposite is y, and the hypotenuse is 1. So y divided by 1 is just obviously y. Anything divided by 1 is just itself. So in other words, we've got that y is sine theta. So I can label that in here. So I'm just going to say y is sine theta. In the same way, let's think about what cos theta would be for this triangle. Well, the cos of an angle is the adjacent divided by the hypotenuse. The adjacent side for this one is just x, and the hypotenuse is again just 1. So in other words, x is cos theta. So I'm just going to label this here, x equals cos theta. So why bother with this? So if I just take this and give myself some more space down here and think about using Pythagoras now. So if we apply Pythagoras to this right angled triangle, what we'd see is that this side squared plus this side squared will equal 1. In other words, x squared plus y squared equals 1. But we worked out what x and y would be in terms of theta. We worked out that x is cos theta, and also we worked out that y is sine theta. So therefore, just subbing in what x is cos theta, and what y is sine theta, we can say that these two things squared and added together must be equal to 1. In other words, sine theta all squared plus cos theta all squared equals 1, because this is y and that is x. So sine theta all squared we write as sine squared theta. Otherwise, that squared could be confused with theta squared. Sine squared theta means we're taking sine theta and squaring the function. So sine squared theta plus cos squared theta equals 1. I'm going to put an identity symbol here. That means it's always true. This is an important result which, as I've said, you'll see time and time again. So it's just basically using Pythagoras on any right angled triangle with hypotenuse 1. this result we're going to use time and time again, and in particular we're going to use this result to prove the cosine rule. So now I've introduced it, we can now crack on and prove the cosine rule. So you've got this diagram in front of you. The first thing I want you to do is to drop down a perpendicular line from angle C down to AB, and just put in a little square there to denote that angle A, the angle here, is a right angle, as is this angle here. Next up, I want you to consider this. I'm going to label in angle A even clearer here, and we're going to think about what the lengths of this side and that side are. So using trigonometry, labeling that this whole length is C, of course, if I just drop down dotted lines so I can section out from A to this point here, and from this point here through to where AB ends at this point B. So this distance here from A to this point is going to be B cos A. This is the adjacent side for this triangle on the left hand side. So if you were to do cos A equals this side over B, this side could be rearranged so this side is equal to B cos A. Try it yourselves if you're not sure. In the same way, we can now work out what this length here is. If the whole length from A to B is given by C, and we know this portion of C is B cos A, then this bit from here to here will be C minus B cos A. Using trig as well for this side length here, from the bottom up to the point C, if this is B cos A, this one here, this will be B sine A. But what we're going to focus on right now is the triangle on the right hand side, this one over here. So I'm going to colour code this in yellow, and we're going to apply Pythagoras now to this triangle I've coloured in yellow. So the hypotenuse is A. So A squared is going to be this side all squared, so that's going to be B sine A all squared plus this side all squared. And this base for this yellow triangle is C minus B cos A. So that's going to be C minus B cos A all squared. So if we expand this out, so B squared is B squared. Sine A all squared, we can write as sine squared A. This bracket here, square the first thing, C squared, we just write C squared. If we're squaring a bracket here, we just double the product of the C and the minus B cos A. So we get minus 2B C cos A. And then it's going to be minus B cos A multiplied by minus B cos A. So we're going to get plus B squared cos squared A. So now what we can do is factorise some things out. So what I'm going to suggest we do first of all is to factorise out the B squared. So B squared, we've got sine squared A from this thing here, but also we've got B squared cos squared A. And so this gives us cos squared A in brackets. Then outside the brackets we still have this plus C squared and the minus 2BC cos A. Now what is sine squared A plus cos squared A? Well, now it's a good time to remind you of that identity I proved a few moments ago, which is this one here. Generally, sine squared theta plus cos squared theta is always going to be equal to 1. And so sine squared a plus cos squared a, instead of having theta we have a, this is also going to be equal to 1. And so this bracket here is going to be 1, so b squared multiplied by 1, that's just going to be b squared. So we have b squared plus c squared minus 2bc cos a. So just to summarise the result, therefore a squared equals b squared plus c squared minus 2bc cos a, which I'm very sure will be familiar to some of you. Oh, I missed out a c there. Oops, that's bad. Minus 2bc cos a. Apologies for that little slip. Thank goodness I just spotted it. So there we go. And we're done. That's the proof of the cosine rule done and dusted. Now let's move on and have a look at proving the sine rule. Now we come to the sine rule. So we're going to start with exactly the same general triangle ABC below. Now what I'm going to do, I'm going to just duplicate this triangle, so I suggest you do the same and just do a copy of it below. I've done a copy of it up here. So the first thing I want to do is to split this first triangle into two other triangles, which I'm going to label as such. So if I just split it down here, this first one, so that this angle here is a right angle, I'm going to label this side x, and I'm going to call this triangle here on the right hand side, I'm going to call this triangle 1, and over here I'm just going to call this triangle 2. Now this triangle here, you have to forgive how it's drawn. I'm not saying it looks like a right angle, but because it's a general triangle not drawn to scale, if you can just suspend your disbelief for me, I'm going to just suggest we call this line from angle B going towards the opposite side here, which is B. I'm going to say this is a right angle. And so this is going to meet the base of B at a right angle as such. And so I'm going to call these two triangles, triangles 3 here, this small one, and triangle 4, the bigger one. And as well as that, I'm just going to make it absolutely clear what angles I'm talking about. So this is angle A, this is angle B, this again is angle A, and this angle up here I'm just going to label, it's clear as day, it's angle C. So now what we can do is think about triangle 1 and triangle 2. So just consider triangle 1. So for triangle 1, x, this one here, is going to be A, this side here, sine B. If you're not sure where that comes from, just remember SOH-CAH-TOA and apply sine. So sine B is the opposite, which is side x, divided by the hypotenuse, which would be A. So it's just a rearrangement of this. So I'm just writing side x as A sine B. Now if you think about triangle 2, we can do something similar there as well. So looking at triangle 2, this one over here, and think about the sine function for this triangle, we have sine A equals the opposite, which again is x, divided by the hypotenuse, but for this triangle 2, the hypotenuse is B. And so from this one, we see that x equals B sine A. So A sine B equals x, and B sine A equals x. So it must be the case that A sine B equals B sine A. So now if we divide through both sides by sine A and sine B, In fact, I'll do it one step at a time just so you can see it. So first of all, if I just divide through everything by sine A, I get A sine B over sine A equals B. Then if I divide through by sine B, I get A over sine A, because the sine B here just cancels, equals B over sine B. And I'm going to call this result 1. I'm now going to do more or less the same thing to this triangle up here, considering the smaller triangles, triangle 3 and triangle 4. And so from this one up here, let's just consider triangle 3. So if I apply the sine rule to triangle 3, the angle in question I've got here is C. And so sine C would be the opposite side. Opposite to C is y, divided by the hypotenuse. If hypotenuse is the side opposite to the right angle, in this case, opposite to the right angle would be A. And so if I rearrange that to get what y is in terms of sine C, we can see that y is going to equal A sine C. But then if you think about triangle 4, this bottom triangle here, and think about the sine function for angle A. Sine A is going to be the side opposite to A, which is y, divided by the hypotenuse in triangle 4. The longest side in triangle 4 is C. So that can be rearranged in terms of y equals C sine A. So A sine C equals y, but C sine A equals y as well. So it stands to reason that A sine C equals C sine A. Then if we divide through by sine C and then divide through by sine A as well, we get that A divided by sine A equals C divided by sine C. And I'm going to call this 2. But we had A over sine A before from result 1. So A over sine A equaled B over sine B, but it also equals C over sine C. So A over sine A equals B over sine B, which also equals C over sine C. So if we put 1 and 2 together, so if we put results 1 and 2 and combine them, we can see that we've actually proven the sine rule. In other words, A over sine A equals B over sine B, which equals C over sine C. And that is the proof, the result of the sine rule. We've got it right there. So before we move on and apply it, just a few pointers. So the cosine rule, if you have a general triangle labelled as such, then besides how you label them A, B, C, and the angles A, B, C, how you label it is completely arbitrary. The size of the angle, or the size of the side, isn't determined by how you choose to label the triangle. The sides will be what they actually are. But from how you label them, these are the different forms of the cosine rule for finding opposite side lengths, and these are different forms for finding the angles you need. Generally speaking, what I would suggest you do is to spot the pattern that, for example, if you're trying to find a side, the side you're trying to find involves the other two sides added together squared. So it's like Pythagoras. So every side you're trying to find It's the other side squared plus the other side squared minus double of the product of the other sides you know multiplied by the cosine of the angle opposite to the side you're trying to find. So A cos A. Trying to find B squared, it's minus cos B. Trying to find C squared, it's minus cos C, and so on. And you can think of the angles as just a rearrangement of this formula. So in terms of finding the angles, you're just making either cos A, cos B, or cos C the subject. And the sine rule, probably a bit more straightforward in terms of seeing where it all comes from. So what we're going to do now is just have a look at these results with a few worked examples. So let's now have a look at thinking of how we're going to use the cosine rule with this worked example I've just unimaginatively called worked example 1. So calculate the length of the side AB of a triangle ABC, in which AC equals 7.4, BC is 9.1, and angle ACB is 105.6. Give your answer to 3 significant figures. Okay, what I would suggest we do for this one is just to draw out the triangle. I cannot picture it without drawing it out. So we're told that AC is 7.4. So my suggestion is, just with a ruler, just sketch in somewhere a straight line and label it AC. So I'm going to call this one, whoops, let's scroll up slightly, there we go. So yeah, I'm going to call this one AC. And I've been told that from A to C is a length of 7.4. From B to C is 9.1. So again, it's got a common point of C. So I'm going to just draw a line from C and put it down here. I'm going to make it arbitrarily longer than AC because 9.1 is longer than 7.4. So I'm going to put it maybe somewhere here. That'll do. I'm going to call this point B, and from B to C, we're told that's 9.1. Now I'm just going to draw up the missing side, just to complete the triangle. We're also told that angle ACB, the angle at C, is 105.6. So I'm just going to draw this in here. This angle is 105.6 degrees. So we want to find AB. So we're after this side here. So at this point, I'm just going to remind you of that table I showed you earlier in case you should find that useful. So there's the table from before. So we can see here we've got this triangle, which is by chance pretty much exactly what I've drawn in. That was a fluke, by the way. I'm not going to say that was deliberate. You're probably thinking, oh, I meant to do that. I didn't. I'm not that clever. So we're wanting to find this one AB, which down here, if you want to use this method, is C. So what I can do, I can call this side C, like so, and then I can use this formula here and just square root the whole damn thing to find out what C is. And so side C is going to be the square root of A squared plus B squared minus 2AB cos C. So this is going to be side A, and that's going to be side B. And so C squared is going to be A squared plus B squared, which is 7.4 squared, minus 2 times A times B times cos of 105.6. That would find us C squared, but we want just C, so we're going to square root this whole beastly thing. A bit of calculator bashing and we'll get what we need. So let's get the class whiz out, type this in. So it's going to be the square root of 9.1 squared plus 7.4 squared minus 2 times 9.1 times 7.4 times cos of 105.6. Close brackets, press equals and hope for the best. It comes out at 13.2 centimetres to 3 significant figures. And so that's the answer we're going to write down. That is what we need. So 13.2 centimetres in brackets to 3 sig figs. Question 2, it says to find the size of the smallest angle in a triangle whose sides have length 3.5, 5.2 and 2.8, and it says to give your answer to the nearest 0.1 of a degree. And so what we're going to need to do here is what I mentioned in one of the warm-up questions. And I'll refresh your memory on that in a moment. But first of all, what I want to do is just to draw this one out. Okay, so I'm just going to sketch any triangle here. Again, I can be an examiner now and just use the get out of jail free option, but it's not drawn to scale, so leave me alone. Don't criticise me for drawing it badly. Examiners love to do that. So, one side is 3.5, so I'm going to call this one 3.5. The other one is 2.8, and the longest side is 5.2. The smallest angle, remember from for warm-up question 3, the smallest angle will always be opposite the shortest side. So for this one, the shortest side is 2.8, and so the smallest angle is going to be opposite this shortest side. In other words, this one here, which I'm going to call theta, that's going to be the smallest angle because it's opposite the shortest side. 2.8 is shorter than 3.5 and is definitely shorter than 5.2. So we're going to try and find theta here. Okay, and again what we can do, if you wish, we can use the general table here. We don't need to, but you can if you'd like. What I'm going to suggest you do, just to sort of move you away from relying on remembering more than you have to, is just to think of it like this. If you know all the sides of a triangle and you want to find an angle, the angle you're trying to find using the cosine rule is just going to be cos minus 1. Okay, so it's going to be cos minus 1 because it's inverse cosine rule, if you like. And it's always going to be the two sides that are on either side of your angle squared and then added together. So add together the two sides that flank the angle. You then minus off the side which is opposite to the angle you're trying to find. So for that reason, we're minusing off this 2.8 squared. And we're going to do all of that divided by 2 lots of the product of the sides which flank the angle you're wanting, which are 5.2 and 3.5. If you prefer to use this, you absolutely can do. That's no problem whatsoever. What you should get for this one, let's see in fact. So cos minus 1, 5.2 squared plus 3.5 squared minus 2.8 squared divide by 2 times 5.2 times 3.5, close these big brackets. The answer you should arrive at, to 3 sig figs no less, is 30.2 degrees. It's just a case of experience and practice in terms of getting these and finding them as easy as you possibly can do. So let's move on now to question 3. So question 3 is a plane flying from an airport on a bearing of 20 degrees for 180 kilometers, and then on a bearing of 110 degrees for 230 kilometers. Calculate the distance of the plane from airpoint A. Give your answer to the nearest kilometer. And again, this is a question where no triangle has been drawn for us. If you're particularly good at picturing things in your head, maybe you could do this without drawing a picture of a triangle. If so, you're much better than me. I don't mind saying that. So unless you're a super visual genius, I would suggest to all of you to sketch out this on a diagram. So it's starting off from airport A. So if I just call this A, remember bearings are always measured from north clockwise. So if that's north, bearing of 20 degrees, that means it's going to go in this sort of direction. So it goes there and it travels along that distance for 180 kilometers. So that's 20 degrees and that's 180 kilometers. Now, after that, it then goes on a bearing of 110 degrees. So again, if I just draw a line going upwards for north, after travelling for 180 kilometers, it's now going to turn and head on a bearing of 110 degrees. And it's going to go on that bearing for a bit longer, for 230 kilometers. So 110 degrees, that's about 20, 45, 90 would be straight across, but it's more than 90, it's 110. So 100 might be about here, say 110, about there, like so. And it ends up at this point. So I'm going to label this 110 degrees. And this distance is 230 kilometers. So by doing a carefully constructed sketch, we're actually going to find this much easier than what we think. I'm just going to complete this to make a triangle. And I'm going to just use a bit of simple GCSE geometry now. So we know this is 20 degrees. I could do with finding out one of these interior angles. And what I'm going to do here, I'm just going to drop down a dotted line like so and use the idea of alternate angles. So you should remember from GCSE, I call them Z angles. So if this one's 20 degrees here, this one here will also be 20 degrees. Remember, alternate angles are equal in size. So that's 20. That's going to be 22. 22, 2, double O. Not 22 degrees, 22, 20 also. In case that's ambiguous. So, and again, angles on a straight line. If that's 110, this bit here will be the extra 70 degrees. So actually, not only is it easier than you thought, it's actually particularly easy indeed when you piece together the pieces of this puzzle. This angle here, that bit of it is 20 degrees, this bit here is 70. So what we've actually got here is a right-angled triangle. So I can simplify this much more and just draw out a right-angled triangle. Yeah, I know I can't sketch for toffee, this is absolutely awful. That's meant to be a right angle, doesn't look like one at all. But my get out of jail free card, it's not drawn to scale, so leave me alone. Don't bully me. So that's 230 kilometers. And that's 180. The moral of the story, always hunt for the easiest solution. This one actually isn't a sine or cosine rule at all. This one's just simple Pythagoras, funnily enough. And so the distance of a plane from airport A. So this is airport A. This is where it ends up. And so the distance of this plane from airport A is just this distance here, which is the hypotenuse of this right-angled triangle. So I'm just going to call this x. And just apply Pythagoras. Couldn't be any easier. It's going to be the square root of 180 squared plus 230 squared. That's a very ugly looking plus sign. That's a bit better. So we're going to evaluate this and give it to the nearest kilometre. So let's see what this is. So it's going to be the square root of 180 squared plus 230 squared. 10 root 853. What on earth is that? Press SROD. Ah, this makes more sense. So to the nearest kilometre, 292 kilometres. And that's all there is to it. You could have, if you wanted, used the cosine rule and done minus 2 times 180 times 230 times cos of this angle here. But what's cos 90? Well, cos 90 is 0. So the minus 2 BC cos A bit would have disappeared. So again, like I mentioned before, the cosine rule is a generalization of Pythagoras. Another way of thinking about that, Pythagoras' theorem is a particular case of the cosine rule. So we've done the cosine rule, let's move on now and consider looking at the sine rule together. Now for the sine rule. Now the good news about the sine rule is I do think it's definitely easier. I don't know if that's opinion or fact, but it's so much easier than the cosine rule, I really do think that. So example 1, triangle ABC, we're told the lengths of AB and we're told 2 angles. You need to find BC a different length, give your answer to 3 sig figs. Now again, I can't picture this without drawing it. So let's just do this sketch. So we're told AB is 8 centimetres. So I'm just going to sketch in a line, and I'm going to label that AB, and its length of 8. What else have we been told? So we're told BAC is 35, and the ACB is 50. So I just need to complete this triangle really by just doing something like this. If that's A and that's B, it stands to reason I need to label this one at the end C. Now what angles do I need to label? So we've got BAC, so the angle at A is 35, so I need to label this one here 35 degrees like so. And the angle at C is 50, so that needs to be labelled 50, like I'm doing now. So find BC. So BC is this side here. So, sine rule. I'm going to show you what you can use if you really want to. I don't think this is necessary, but just to return to what I showed you in one of the previous sections of this video, we can use this if you really need to. I'm not going to pay attention to that too much, okay? I'm just going to think about the side I want to know. So I'm going to call this side x, because that's the mystery I want to find out. So if I want to find a side, alright, the side I want to find divided by the sine of an angle, the angle opposite to it. And what I need to know now is another side I know, which is 8, divided by the sine of the angle I know opposite to that one, which luckily I do know, which is sine 50. So I can use a sine rule because I know enough information. So side I want to know divided by the sine of the angle opposite to what I want to know equals another side I know divided by the sine of that angle opposite to the other side I do know. So I can just rearrange this now by multiplying through by sine 35. So x is going to be 8 multiplied by sine 35, all divided by sine 50. So if we just bash this into our calculators and round to 3 sig figs, we've done it. So 8 sine 35 over sine 50, close brackets, that goes to me as well, close that off. We get 5.99 centimetres. And I'm going to mention here that was to 3 significant figures. So that's all there is to it. So if in doubt, do yourself a nice, clear sketch and label it in correctly. Let's have a look at another one. So here we've got triangle DEF. DE is 4, from E to F is 9.5, and the angle at D is 70. We need to find angle DEF to the nearest 0.1 of a degree. So DEF is the angle at E, which is this one here, which I'm just going to call theta. Now, it might seem we have a problem, because I don't know the side opposite to the angle I want to find. So what do I do? Well, we need to just think slightly around this. We know this side here, and so what I could do, what we need to do actually, is to find this one here, which I'm going to just call alpha. And once we found alpha, we can use the angle sum of a triangle to work out the missing angle theta. So let's do that. So sine theta over 4, sorry, sine alpha, apologies, sine alpha divided by the opposite side equals sine of a angle I know, sine 70, divided by the side opposite to that, which is 9.5. So what I can do is rearrange this and do sine minus 1 of it. So therefore I can say that alpha is going to be sine minus 1, multiply through by 4 beforehand, so it's sine minus 1 of 4 sine 70 divided by 9.5. So let's see what we get for that one. So shift sin, inverse sine function. So we're going to have 4 sine 70 divided by 9.5. And that gives us 23.3 degrees. This isn't our final answer, so I'm just going to write 23.3 ... Never round prematurely. That's not a final answer, this is an intermediate step. But because we know this one now is about 23.3, we know that's 70, we can do 180 minus 70 minus this one to work out theta, because obviously, as we know, angles in a triangle add up to 180. So therefore, DEF, which, just to remind you, I've labelled theta, that's going to be 180 minus 70 minus 23.3. God knows what. Let's see what we get. I'm going to store this on the calculator, so if I press ANS, that answer's stored for me, so I don't need to worry about it. So I'm going to do 180 minus 70 minus that stored answer. To the nearest degree, I get 86.7 degrees. So that's what we have for DEF. The last one isn't so much sine or cosine, it's a compound problem. So it's a multi-step trig problem. So a tourist wants to determine the height of Trump Tower in Chicago, including its spire. So she measures the angle of elevation of the top of the spire at 2 points, 391 meters apart on the ground. So part A is to calculate the height of a tower in meters to 1 decimal place. I'm just going to go out and clarify here, this is not any political statement. I'm not saying I'm a massive fan of Donald Trump. I'm just saying that, right or wrong, he seems to attract attention. We all know who Donald Trump is, so I picked his tower. I'm sure his fragile ego will appreciate me doing his tower a service in this example. If Donald Trump is the sort of person that's watching A-level maths videos for a British syllabus, maybe he'll be very happy. I guess time will tell. I doubt it somehow, but Donald, if you're watching, hello. So, like I say, this is a multi-step problem. How are we going to tackle it? It's actually, in a sense, a simultaneous equation type problem, because we don't have enough information to solve it in one step. So what we need to do is consider it as 2 separate triangles. So what I'm going to do here is just think about this triangle with a 75-degree angle in it. And go down the spire. Like so. So we've got the yellow triangle, and the bigger triangle, in terms of how I'm seeing it, is this one with a 40-degree angle. Obviously, in your exam, you wouldn't need to colour code it as I'm doing here. I'm just doing this to try and show you the differences of what I'm trying to talk about. So there we go. Got a yellow triangle here, the smaller one, 75-degree angle, and a bigger green one, which is the whole thing, which has a 40-degree angle. And so if we just think about the yellow triangle for a second, so we want to find the height of this tower. So I'm going to label the height as x. I'm just going to call this x here. And I don't know this distance along the ground. I've got no idea what it is. And so I'm going to call this, because I'm lacking imagination today, I'm just going to call that distance y, okay? Forgive me if you want to call it something different, you can do. Call it by your name if you so want, I don't really mind. So I'm going to call this y. And so, thinking about the tan function of this yellow triangle, tan 75 is going to be the opposite, which is x, divided by the adjacent, which is y. So therefore, the height of the tower, x, is y multiplied by tan 75. But we don't know what y is, so on its own, we don't have enough information. But we do have this result here. What we can now do, though, is see if we can link this into what we can work out from the green triangle. So think about the green one, and think about the tan function of the green one. So the whole green triangle, just think about the big outside triangle. Think about tan 40. Tan 40 is going to be the opposite side of the big green one, which again is x, divided by the adjacent side. Now for this big green triangle, it's 391 here and y there. So the whole length of the bottom adjacent side is going to be 391 plus y. So therefore, x is going to be 391 plus y multiplied by tan 40. So now what we have is two different equations, both involving x, both involving the height of the triangle. So what we're going to do now, I'm going to aim to pop these together. So I'm going to put this here and this one over here. Because both of these expressions equal x, we can therefore say that y tan 75 must equal brackets 391 plus y, close brackets, tan 40. So we can now equate these two here. So I can now write y tan 75 equals 391 plus y, close brackets, tan 40. We can now expand out these brackets. So y tan 75 equals 391 multiplied by tan 40. So 391 tan 40 plus y tan 40. All I'm doing here is just multiplying out brackets as I would do for any algebraic question. So 391 tan 40 plus y tan 40. I'm now going to subtract y tan 40 from both sides. So y tan 75 minus y tan 40 equals 391 tan 40. Here now I have a common factor of y, so I can now factorise this. So y brackets tan 75 minus tan 40 equals 391 tan 40. So now we can solve this for y. So y is going to be 391 tan 40 divided by this thing in brackets. So 391 tan 40 divided by tan 75 minus tan 40. So let's use the class whiz and see what we get for this one. So, fraction button, 391 tan 40 divided by tan 75, close brackets, minus tan 40, close brackets. We get for this one 113.4094341. Don't round off at this stage, because it's not the final answer. You don't want to introduce any rounding error. So let your calculator do the hard work and store this for you. So I'm going to leave it as 113.409 ... Now what we can do though is, because we've worked out y, which is this, we can now sub this back in to one of these two expressions to work out what x is, in other words the height of a tower. And so because x is y multiplied by tan 75, we can now substitute this in and evaluate the height of this Trump tower. So therefore x is going to be y, which is this 113.409 business, ... multiplied by tan 75. Just to mention again, if you're not sure where I'm getting this from, I'm using this equation here and substituting in 113.409, etc. for y. So the calculator stored this answer for me, so I can then just take this and multiply by tan 75, and we get 423.249, etc. So to 3 sig figs, which is the same as saying to the nearest metre, we get 423 metres. Check that on Google if you don't believe me. that is the height of the tower. Part B, state one assumption made when using this model. There's a few things you could say here. I'd go with KISS, keep it simple, stupid. What's the simplest assumption you could say, which is mathematically valid, which may or may not affect the answer, depending on what the value or the assumption might be. What I would say here is, what springs to my mind, is that we're assuming the ground to be perfectly horizontal. If the ground wasn't perfectly horizontal, this would affect the accuracy of these angles. In real life, the ground is never perfectly horizontal. It might be pretty close, but often isn't quite at all. So I would say the easiest thing to say here is just to put something along the lines of that the ground the ground is perfectly horizontal. Is an assumption being made. It's not the only assumption you could make, okay? You might be thinking, you're assuming that the tower is perfectly vertical. It's not. No building is perfectly vertical. They always list, they lean, and it's only a matter of millimetres to the left or the right. All buildings lean, even if minutely. Sometimes not minutely, for example, the Leaning Tower of Pisa. But no building is perfectly vertical. So that's another assumption you could say. But I think the most obvious one, in my mind at least, is we're assuming that the ground is perfectly horizontal. It almost definitely isn't. Which isn't to say that this isn't a reasonable estimation. So that's all the questions I've got for you today. It's now over to you. So I've merged into this lesson two bits, the cosine rule and the sine rule. This is why it was such a lot to get through. But at the same time, the cosine rule and the sine rule go hand in hand, so it's worth doing them as one, I believe. So exercise 9a, questions 1, 2, 7, 11 and 17, then move on to 9b and try these parts of these questions as well. So do all these diligently, check your answers regularly as you go, and if you're stuck at any point, please do ask me. Do not suffer in silence. Keep working hard, keep doing your homework, and keep in touch. That's all from me. See you for now.